Alright, so today we're doing sections 1, 3, and 1, 4. They kind of go together anyway. So today we're going to be classifying numbers and then talking about the properties of those numbers that we're classifying. Okay? So to put these numbers in categories, these are the terms we use to kind of group them together. When you have a set, that's a defined collection of objects. Okay, such as our third hour class. That's a set of people. Then if we wanted to talk about a subset, okay, that's a set of elements from the original set. So for example, the set is all of you here in third hour. A subset would be all the girls in here, or all the boys in here. Okay, it's a group within that larger group. An element is just an object, so in here it would just be one person. So it's an object in a set. So the set's the large one, the subset's a smaller group, and the element is just one thing within that. So real numbers can be split into two major categories. We have rational numbers, and we have irrational numbers. Okay, let's write down the definition of those before we put some examples in there. So a rational number you can write in the form A over B. So a rational number can be written as a fraction. And to be mathematically correct, we need to say that B cannot equal 0 because you can't have 0 on the denominator of a fraction. Right? I can't write a number 3 over 0. An irrational number is just simply the opposite of that. You cannot. Right, and here's where we'll use our vocabulary from yesterday. So A over B, the word for that was quotient. You cannot write as a quotient. But when you're looking at the decimals, okay, they do not repeat or end. It's not part of the definition of rational number, but maybe you just want to write that note. So here on rational number, the decimals have a pattern or end. So they're just the opposite of each other. So I know that's kind of confusing because that's just all the word part. Let's put some examples with this. So a rational number, okay, can be written as a fraction, like -2/3. It's a decimal with a pattern, such as 0.3 repeating. Now, when you type into your calculator, you usually don't see the bar, right? You see 0.3333333. Right? Or it's a decimal with a pattern, which I'll write down here so I have more room, like 0.121212. You know, and so on. It has a certain pattern to it. So, an irrational number, probably one of the most famous ones would be pi. Because it's 3.14159 and so on. It never ends and it does not have a pattern. Okay? Another one is if you have a random decimal point, 7832, there's just no pattern to it. And it doesn't end. The other famous one we talk about a lot of the time is the square root of 2. So irrational, and even if you're good with vocabulary and you just know what the word rational means, rational, if someone's rational, they're being sane. They're being logical, right? So rational numbers are nice, neat, they have a pattern, They make sense. Irrational, if someone's being irrational, they're crazy. Right? Irrational numbers are crazy. There's no pattern to them. They don't end. They seem like they don't make sense. They're not nice, neat numbers. So within rational numbers, let's start on the inside and we'll work our way out. We'll start with natural numbers. Those are sometimes called your counting numbers. That starts with 1, 2, 3. Those were the first set of numbers developed in math. Then they built on from there. One more step was whole numbers. What they did there then was they added on the 0. So that's the difference from natural to whole. They add on 0, the absence of something. Well, then they went one step further to integers, where they added on negative numbers. So they have -2, -1, 0, 1, 2. They have positive and negative numbers. Now in your homework, they'll try and trick you. They'll write -10/5. Because really -10/5 is what? -2. Okay, so even though they write it a little bit different, that's still what that is, right? Or like -√16. Because what's the square root of 16? So it's really -4. So it's still within that category. So you might have to simplify it a little bit in your brain before you put it in the right category. Okay. So that's just how it builds. Naturals, 1, 2, 3. Whole numbers adds the 0. Integer adds on the negative. Okay, and then rational extends into decimals and fractions that aren't simplified to whole numbers. Okay, so the big scope of that's called real numbers. That's just the category of what we just talked about, the rational and irrational. So it's like a giant Venn diagram with all these sets built within it. And we do call them real because when you get to Algebra 2, you'll talk about non-real numbers. All right?
Numbers that don't exist?
They're called imaginary, yeah. Yeah, that's coming in Algebra 2. All right, so we might have to flip back and forth with this. So let's match these into the right subset. Okay, and I think the easiest way to do it, because they want you to list them all out, is to start in the middle and work your way out saying, is it in this set? Is it in this set? Is it in this set? Okay, so Chloe, what really is the square root of 36? Because they're trying to trick us here. 6, right? So when we look at 6, would 6 be in the set of natural numbers? Yeah. Now, what do you know about a Venn diagram? If it's in this one in the middle, it's also in every other one on the outside of it, right? So if you're in the middle, you're in all those other ones, those subsets that are embedded within it. So yes, it's in the set of natural numbers. So really when you find the first one, you just write all the other ones that ripple out from there. So then because it's in there, it's also in whole, it's also in integer, and it's also in rational. Okay, let's look at 0. Is 0 in natural numbers? Is it in whole numbers? Yes, so now we write from whole numbers out. So we're going to write whole, integer, and rational because it's embedded in all those sets. All right, they're trying to trick us again. Jared, what is -12/6 simplify to? So let's look at -2. Is that a natural number? Is it a whole number? Is it an integer? Yes, so we write from there out. So we write integer and rational.
whatever it is, you just kind of go out from there to
Mm-hmm.
rational part.
Yeah. So that's why I think this visual is really helpful. So square root of 2. That's a weird 1 point something 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 something. Right? And I kind of gave you a hint on that one. So that's not a nice number. So already you're just an irrational number. You're on this side. Now, if you weren't sure, you could type that in a calculator and check. Because, for example, 3 over 10, do you know what a decimal is for 3/10? 0.3, right? So that's a nice number. It's written as a fraction. It ends. Okay, so that's why it makes it a rational number. It's a nice decimal. So when you're at decimals like that, you're all the way out just to rational. Anyone have any questions about using that chart and figure out which set it's in? I think it's pretty easy. When you find the first one, you just write all the other ones out from there. Alright, this is the second section that we're putting in here today. So now when we have all these numbers, what are the properties we can use with them? This, right, should look familiar. That was from that matching activity that you guys did the first day on here. This was those properties that we had. So here's what makes these properties work, is that when you transform it, you get an equivalent expression. It's the same thing, just written a different way. Okay, so the definition for this is 2 algebraic expressions that have the same value for all variables. Fancy way of just saying it's the same thing written a different way. Alright, so let's go through these properties. And I know Mrs. Harden and I, when we were walking around helping you guys get that right on the matching activity, we gave you some hints on how to figure these out. The commutative property, right? When you commute back and forth to school, you go to school and then you come back from school. It's a back and forth thing, okay? When you know that word, it kind of helps you. All this is then is changing the order. It just switches. Change the order. So with addition, that looks like if you do a plus b on this side, it doesn't matter if you add them backwards and you do b plus a. Right? 3 plus 4 is the same as 4 plus 3. Same thing with multiplication. If you want to do a times b, it's the same thing if you wanted to multiply them backwards and do b times a. Now notice there's not one on there for subtraction, because 4 minus 3 is 1, whereas 3 minus 4 is negative 1. So you cannot flip-flop subtraction, only addition and multiplication. Alright, associative. When you associate with someone, you hang out in groups with them. So this one is just changing the groupings. So this is the one that has parentheses. So if we wanted to add A, B, and C together, and we said, oh, we're going to add A and B first, and then we'll add C on. That's no different if the second time we're going to add B and C together first, and then we'll add A on last. Right, you can change the grouping with addition. It doesn't matter. Because it's commutative, it all gets added up in the end anyway. It's the same thing with multiplication. You can do A times B and then multiply C. Right, 1 times 2 and then times 3. That would be the same as doing 2 times 3 and then multiplying the 1. So just know, order doesn't matter for adding or multiplication. Okay, the identity property. When you talk about your identity, right, that's who you are. So identity means it stays the same. Okay, I'll say a fancy word here. Obtain the original number. Okay, the original number doesn't change. It stays true to who it is. So for adding, if you want to take a number and you want to add something so that it ends up A, what do you have to add to that number so it won't change? 0. Good job. Now, when you want to multiply this with something, what do you multiply a number with so it stays the same? 1. Good job. It's got this. Inverse, when you talk about being inverted, right? Like if you're on a roller coaster that inverts, it's upside down. Okay, so these are things that like undo each other. So if I have something and I want to add something to it so it adds up to 0, what do you have to add to a number so it'll come out to be 0? The opposite of it, right? So that's where you throw a negative in front of it. Right? You want to do 3 plus negative 3. You want to do 7 plus negative 7. The opposite of it. When you multiply, you want to end up with 1. So if and this is where, kind of going back to your fraction stuff, if I want to end up with 1, so if I had 3 and I wanted to end up with 1, I really want to divide by 3. So another way to represent that would be 1 over that number. Because dividing by 3 is the same thing as multiplying by 1/3. Dividing by 2 is the same thing as timesing by 1/2. Alright, these last two only apply to multiplication, so just put X's in those boxes there. 0 property of multiplication, it's just what it means. You always get 0 when you multiply. This is something that, this property is the foundation for when you solve with factoring in chapter 9. Okay, when you multiply something with 0, it's always going to be 0. That means one of those things in there, in that multiplication problem, had to be 0. That's the only way it spits out 0. Same thing here with negative 1. This gets you, you obtain the opposite number. Right, so if you take negative 1, multiply that out with a number, you end up with the opposite of it. If I take negative 1, multiply it with 3, I end up with negative 3. If I take negative 1 and I multiply it with negative 5, I end up with positive 5. You get the opposite. Alright, example 2. This is so important. This is something we see people do all the time. It is such a common mistake. These two things mean something totally different. Totally different. Right? And I'll probably do one with just numbers, so maybe it's a little bit clearer. When you have this, you could split this up in example A, and you could pull that y out and just have 6x over 1. That's why that would just cancel out, because y divide y is just a 1, and you'd be left with 6x. This, when you split this with that plus sign, this means 6x over y plus y over y. This is still over that y in this one. Okay, so when that simplifies to a plus 1, okay, so really what we want you to know from that example is you cannot just cancel out if there's a plus or a minus on the top of a fraction. Okay, you cannot just cancel something out if there's a plus or minus on the top of a fraction. That's such a common thing we see. and that's just the algebraic reason why there. Okay, let's see. Okay, any questions on that?